Welcome to the second short recorded video on numerical integration in the Part B lecture notebook for the Computational Applications module, module number 4 in Math 1376. In this notebook, in this video, we will be discussing geometric or deterministic methods for numerical integration. Now, many of the deterministic approaches to estimating integrals are based on partitioning A. Remember, A is this set that we integrate over. I discussed this in this notation above. I'll go to here, where we are integrating a function f of x, and we think of integration as a type of aggregating behavior involving an infinite summation, which is denoted or inferred by this long script s for like summation, like an infinite summation of a function f of x over a set A. And if you had a set A that was in the domain of the function and you wanted to integrate it, one geometric-based approach would be to cut up A into a bunch of non-overlapping sets. You could allow for the boundaries of these sets to agree, but the interiors to not overlap. And then you would try to approximate the area or volume that's related to the integral of the function over these subsets using simple geometric approximations by using shapes that approximate the region basically between the curve or the surface, whatever the function is, and the axis or plane that you're integrating over. And you want to use objects that are simple to compute the areas or volumes of. So in 1D cases, what we typically do is use rectangles or trapezoids, because these are objects that have areas easily computed from rules that we know that we're familiar with from previous classes. So when A is this interval, as we're going to restrict ourselves to 1D cases primarily, then we're going to partition A typically into equally sized subintervals. This doesn't have to be the case, but typically it's equally sized subintervals with a length that we typically refer to as a delta x, which is why in the code you'll see I have this variable defined as delta x. And this will be used to approximate the signed area of f of x over each subinterval by using a rectangle that's as wide as delta x on each subinterval and whose height is given by the evaluation of f of x at some point in the subinterval. And what are natural candidates for evaluating the height of f of x? Well, you could use the left endpoint, which is what we do here if we use a left-hand rule, as it's called. We could use a right-hand rule and evaluate f of x at the right endpoints, or we could look at the midpoints of each subinterval, and we could use those as the heights of the function. Now, you could use any other point as well, but these are typical rules that are used because they are simple to encode using array slicing. And then based on whichever rule you pass, let's say to a function, compute rectangle rules for a given function over an interval a to b with a number of rectangles in that you want to approximate. You could get the intervals that you want to create on the x-axis, the horizontal axis. And then based on what rule you pass as a string, left, right, or otherwise it would be considered the midpoint rule, you could then say here, return the heights of the corresponding rectangles you use, and then just add it all up. Sum up all of those heights multiplied by delta x will be a summation of the areas of these rectangles. That's what this function does. And we'll return to these evaluations when we do some visualization so you see it. A useful suggested activity is for you to add a docstring and doctest to this rule, but you might want to go through the code first in this video before you add that for yourself. So I've already run this here, so I'm going to skip running it, but you should run it as well. And now we're going to do some numerical experiments and analysis to understand this. We're going to first show how to use the compute rect rules function defined above with the default rule of left. And we're going to analyze the rate of convergence, the ROC for short, how quickly this seems to converge to as n increases, the number of rectangles increases, to the actual integral. And we're going to create some interactive visualizations just to help us tell a story and make more sense conceptually about what's going on. So I'm going to use the same function that we saw in the first video and at the beginning of this lecture notebook, which is x plus 1 times x minus 5 times sine of 3x. Now I'm going to compute the approximation to the integral. So I'm not passing a rule, so I'm using the default left one. I'm going from 2 to 4, and I'm using 10 rectangles, and I'm returning the fourth argument because of Python indexing at 0. So this could be 3, this could be -1 because it's the last output you have from this tuple that's returned. So however you want to do that. Now, why am I only returning that last one? I'm only interested initially in looking at this integral approximation. These other values are really useful for plotting. So I return them anticipating that I'm going to be plotting later, but I don't need them right now when I'm just studying the integral approximation. Now, when I approximate this and I print that integral approximation, which is this output that I've stored, I see negative 1.70 approximately. Now, you might recall from this previous video and above this notebook that when we looked at that same function and we used the very accurate numerical quadrature method within SciPy to integrate, we got a value from 2 to 4 of negative 1.72. So negative 1.7 is a pretty good approximation to negative 1.72. And you could even play with this n here. You can make n, let's say, 100. And there you go, negative 1.72. It seems like it's a very good approximation with 10 or 100 rectangles. And so I'll go back to 10 here. Now, if we want to study how quickly this converges to the actual value, then we want to study the rate of convergence, ROC for short. And to do that, we usually vary critical inputs. So I'm going to switch that back to before. Over orders of magnitude and employ log-log plots to understand how errors are reduced by refinement of inputs. So to understand this in practice, here I'm going to just run this here, print this in. So this is how it will show up for you when you see it. I'm going to use the log space function because it's an easy way to create an array that varies over orders of magnitude, which is really what you want to do when you're studying rates of convergence. You want to vary inputs usually over orders of magnitude. And so I'm going to create an array of n's that go from 10 to the first to 10 to the fourth, and I'm using the log space function, not linspace, to do that. So from 1 to 4, and with 4 of these, I'm going 10, 100, 1,000, 10,000. So if you look at this, this is a float 64. You notice the dots here. This is a floating point set of inputs. So an easy way to fix this, because I'm assuming when I pass in here, if you look at how in is used, it's used in a linspace, right? However many rectangles I use when I pass a particular fixed in to this, then this needs to be an integer for linspace to work. So the way that I do that is when I create this log space, I then cast it as a type int. So now I have 10, 100, 1,000, and 10,000. So now I create a simple loop to loop over the arrays for each of the n values in that array of n's. I have this empty list of int approximations, int approxes, and I append to that list the approximation that's given with the particular n value. So the first time it loops through, it will be the approximation with n equals 10. The second time it will be with n equals 100, then 1,000, and then 10,000. And it will create this list of approximations. Now, in order for me to compute the errors, and you can see these approximations, negative 1.7, negative 1.72249, negative 1.72134, negative 1.72119. So they are changing in the later significant digits, these approximations. And if I want to compute these areas against the very accurate quadrature numerical integration of this function given by the quad function, which is something we saw in the first video. Remember, I only want to return the first input from it because that has that approximation from the integral approximation given by the quad function. I cast this list as an array so I can take and subtract a value from every component. So I take np.array of those integral approximations, and that gives me the errors according to the left-hand rule. If I look at those errors, I see that they're on the order of 10 to the negative second, 10 to the negative third, 10 to the negative fourth, 10 to the negative fifth. So they do seem to decrease by an order of magnitude as I increase n by an order of magnitude. If you use a log-log plot then to visualize this, you may have to make sure that you plot the absolute value of the errors because it's a logarithm. You need to make sure that you're not asking to take the logarithm of something that's negative. This gives you a sense of the absolute value of the errors and how they decrease as you increase the number of rectangles. And this gives you a good visualization of the rate of convergence, which we define in terms of basically the slope of this line if you could approximate it by a line. Kind of looks like a line. It decreases linearly. And how do you best estimate this? This is going back to something we saw way early on in this course in a module where we use a polyfit function within NumPy for the log of the n's and a log of the absolute value of the errors. We fit a line to it and we return the slope of that line. And this gives us an estimate of the rate of convergence. And when we look at it, we see -1, which means the error decreases by about a single order of magnitude for every order of magnitude increase in the n value. So this is a way to quantify what we're otherwise kind of qualitatively seeing here and through kind of a visual inspection of these errors. This gives a better estimate of what the actual rate of convergence is, which seems to be about, or it's a first order accurate, meaning that the error decreases by about 1 order of magnitude, and that's why it's -1 here. The error is decreasing as we increase the number of rectangles. That's why the slope is negative. So we can do some fancier visualization to also understand what's going on with the rectangle rule. So here I want to plot the rectangle rules. Again, I'm giving a function f, a to b, which will be the interval of integration, the number of rectangles that I want to use, a rule, and then xmin and xmax for visualization. Maybe I want to plot beyond my interval of integration, controlling the fig num. And again, I'm going to return all the outputs of the compute rectangle rules. So this is all that information from that function that we saw above. I'm going to get an accurate integral approximation so I can describe the error in my plot, and everything else below is just for plotting. All right, and this is the type of plotting stuff we've seen below, where I also now create some patches, but now instead of shading the area under the curve, I want to create patches according to the rectangles. So I create a list, an empty list of rectangles. I append to that list rectangle patches, right? And you can say, what is this rectangle? What does that mean? Where does that come from? That's from here, which hopefully you ran, otherwise nothing's going to work. From the plotting toolbox, the matplotlib, from the patches subpackage, I've been importing polygons, rectangles, patch collection. So all of that is useful for the visual storytelling of integration here, where I have this collection now of rectangles and I want to plot all of those together. So it's actually not too much code to plot a bunch of rectangles, and then I have some additional annotation in terms of the title of the plot. So let me create that function and let me show you this widget that is interacting with that rectangle rules plotter, which then calls the compute rectangle rules function. And so if I run interact here, you can see this is with n equals 3, right? And I'm going to make this a little larger so that things show up nice. There we go. So -1.72 is the approximate integral. We're getting that from the quad function. The sum of the rectangle areas is -1.35. This is n equals 3. And look at that. Like that's of course terrible. -1.35 is not a good approximation of -1.72. But if you go up to like n equals 7, you see there's 7 rectangles here. That's from the patch collection I'm plotting. -1.67 has gotten closer to -1.72. I can make n 10. And already -1.7, it's a better approximation. Now you'll notice any given rectangle is not necessarily a good approximation. These rectangles seem to underestimate what the signed area is in terms of this part of the curve, but over here it's overestimating. And so the overestimation errors I'm making here seem to be canceling out these underestimation errors. Similarly over here, I'm overestimating the area here, but underestimating, and there's a cancellation of errors. Of course, the local cancellation of errors decreases as you use more and more rectangles. Like if I go up to 30, you look and you see, oh, these rectangles are now better and better approximations to the area associated with the little subinterval that's associated with using 30 rectangles instead of, let's say, 3, 7, or 10. Now, if you go back down to, let's say, 3 rectangles, you'll notice again I'm using the left endpoint, left, 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 to get the height of the rectangle. That's corresponding, again, to this function. Using the slicing going from the height of the rectangles going from the first value of this lens space that I'm using to describe the subintervals for the rectangles, and I go up to but not including the last one, and that defines the height of the rectangle. So that gives me the value at all the left. If I switch to right, I start at the right endpoint, so I start at the second value of this range of indices of x, these ix values that are used for integration. That's why the ix is there. And I go from 1 all the way to the end, so it includes the last endpoint. And then this takes the up to but not including the last one, but then I add half the distance, half the width of each rectangle to each one to get the midpoint. So just when you see that in the code, and now you look at the plot, hopefully things make sense. If I take left and turn it to right, what you should see is this value here should become this value, and it should be down here. And this value right here should become this value. Like for this rectangle here, it should come up and over. And then this rectangle right here, this will be evaluated at this point right here. I think it should have that height. So let's just see. There you go. You're using the right endpoints now. And you can again see if I increase n, I get decent approximations for larger and larger n, negative 1.71. Now, if I come back down to 3, I run interact. Let's say I go down to the middle rule. And then you can see already with, that's with 5. Here, let's go down to 3, just so you can see. Run interact. Negative 1.94, it's not so great. Negative 1.94 compared to negative 1.72. But if you looked at left, negative 1.35, that's 0.4 off. The right one is 0.5 off. And the middle one is only 0.2 off. So the middle one seems to be a little bit more accurate even with a small number of rectangles. And if you go up to 10, negative 1.74, it's off by about 0.02 like we saw previously. But in general, the midpoint rule will in general be a little bit more accurate because it's kind of balancing the local cancellation of errors. You'll see each rectangle is kind of locally approximating, over approximating and under approximating over half of the interval. That's kind of why people prefer to use the midpoint rule, is it just makes things a little bit more accurate generally, and it converges faster, as we will see. So well, actually, I think that's something that I have you explore in your activity. But we visualize approximations of the integral for a different function below. So here's x squared function. So I'm just going to run interact here again. So I'm looking at it x squared. I'm going to go from 0 to 1 for my integration. And you can change these, of course. X min and x max are negative 1 to 2, and n is 10. One thing I want to point out is just if you look at this plot, when the function's increasing, when it's an increasing function and you're using the left-hand rule, you will always produce an underestimation. Notice it's 0.29. Whereas if I use the right-hand rule, it will overestimate because now it's using the larger value on each subinterval, 0.39. And now when I use the midpoint rule, again, it's a better approximation because, again, there's a little bit of over and underestimation on each subinterval, so the errors are kind of canceling out. And again, you can play with this. You can play with, I encourage you to play with this. Change this value to less, make it like 2 or 3, change how you're plotting it. Interact with this, the experiment. Now, here's a rectangle rule class as a subclass of integration. The integration class was defined in the first part of this notebook, and it was also covered in the first video. So I'm subclassing from integration. When I initialize, I'm calling the superclass, the integration class, and I'm initializing that with f and a and b. But now there's some other parameters here. N, which is not part of integration before, because now we're talking about integration rules using rectangle rules. And I'm going to default the rule to left, which you can always overwrite by changing how you do the rectangles with a different method. This just sets the parameters for the rectangle rule in terms of N and rule. If you wanted to change A and B, you have that method. It's inherited from the superclass, which is the integration class that had and I'll just show it up here. I scrolled too far, excuse the scrolling. You could set the integration limits with a method from integration. And so that's inherited in this subclass of rectangle rule. Okay. Then I just encoded the compute integral approximation as a method within this class. Notice I just have the self.iy, self.iy. You just have to change some of these variable names. And I'm using the left, right, and mid. This just looks very familiar from the compute integral. And then I'm also encoding the plot rectangle approximation in the evaluate and plot rectangle approximation methods within here. And again, you can go through this. I don't want to belabor this because I'm not asking you to actually necessarily do anything with these classes. I just want to give you more exposure to how you can use classes to help collect a lot of methods and data related to a problem in a very well-organized class object. And, explore it, add some doc strings and everything, but none of the activities are requiring you to work with these classes. However, I highly encourage you to do the activities with the classes by editing them, but you don't have to. So now I created that class. I'm not going to really go over the details too carefully. And then I'm going to create this rectangle rule instantiation for f-rex that I call it, again with our favorite function that we've been seeing, x plus 1 times x minus 5 times sine of 3x. And now I'm going to look at the evaluate and plot rectangle approximation function method within it, just as usual, so you can see how to play with that class. And notice here I changed x and min and max from -1 to 2, whereas previously the plotting with this function was from -1 to 5. And you could make those values things that you change as well with your interact. I just fixed them. And this just allows you to kind of zoom in where I'm restricting A and B a little bit. And you could just see how well, like in this case, when I'm integrating from 0 to 1, my integral is now -4.49. And let me just enlarge the figure. So -4.4 with the sum of rectangles. And if I increase it, wow, look at that. That really shades it in from -1 to, or from 0 to 1, -4.49, -4.48. So that's it for this video. It's just to give you some more exposure to playing with these objects, experimenting. I really want you to work with it. There's a solution video for this activity with rectangle rules. For the sake of simplicity, again, this activity does not require the use of any classes, although I encourage you to maybe think about how you would approach it with classes, but it's not necessary. There's a solution video for this that doesn't cover any of the things with classes. It's based on kind of an older implementation of this that just did the functions. But I want you to look at the different rates of convergence, and you should see when you do this that the rate of convergence is faster for the midpoint rule, that it looks like a -2, whereas the left and right is -1. So that's it for this video. Thanks for listening.